very quickly, we can just try to fill that, I thought, I did that this morning, and I thought it might be useful to kind of summarize all the quality of service mechanisms for all the standards. So in terms of classification, what is the classification for the case of 802.11? There's no classification. There's no classification. We don't have any quality of service awesome for 802.11. We don't have. For here, we do have classification, right? So for here was based on what? Was based on TC and TS. So these traffic classes and traffic specs or T specs, we can support some classification. For 802.16.1, again, it's based on connection ID and it's based on service flow ID. And I think in 802.15.1 there was some also traffic stream kind of ID as well. I can't remember the exact name. Okay, so the only one that does not have any classification is 802.11 because it does not support any quality of service. So channel access mechanism. Well, here, DCF, we have two things. We have DCF and we have PCF. DCF uses a SISMA CA. PCF, pulling. Okay, so this is the channel access. For 802.11e, again, we have eDCF and we have PCF. So what is the channel access for eDCF? Well, again, it's SISMA CA. It's the same. So we have collision. We still have collision here, right? For eDCF, we have SISMA CA. It's still SISMA CA, but based on. So when we. HCF, yes. HCF is again based on pull. Okay. Type. Here we have only one mode, which is channel access mechanism is based on TD, D, TDMA. Okay? And here again, or FDD طبعا. Here it's based again on TDD, TDM. Yes, okay? Okay, let's get to the tricky stuff. So packet scheduling. For 802.11, what is the packet scheduling? مفيش حاجة اسمها no packet. We have to have packet scheduling. ها؟ FIFO برافو عليك. دي فاكرة. So it's FIFO. Which means that when I have a traffic within one node, here we're talking about intra-station scheduling. So within one node, do we actually distinguish between the different traffic? No, we don't have any way of distinction. If we have multiple classes, okay, then we can talk about priority-based queuing, because depending on the class, you can take a priority. So in fact, for 802.11e, you can call it priority-based scheduler. Because depending on the class, even for eDCF, you still have classes, right? And for HCF, you have traffic specs, so you have flows. So depending on the flows or the classes, you can have different priority. So within a node, I can let the packets coming from a specific connection or a specific flow to go first, right? So in that case, there is priority based. Also here, right? Because here, there are some traffic classes. So only 802.11 does not have any classes. It's not actually defined any class. So there is no priority-based queuing. So for enter, for 802.11, what is the? Well, I can call it broadly, again, FIFO, because it's, again, there is no distinction. So whether the traffic coming from this node or from this node or from this node, I don't have any distinction. So it's technically, again, FIFO. Here, can I specify a specific enter station packet mechanism? Well, it's based on pulling. So it's dictated by the polling sequence, right? So based on the polling sequence, I can get node 1 first or node 5 first, or so it's priority based in a way, okay? But it's dictated by the polling. So polling can make it round robin, in which case it's FIFO. Round robin, which means node 1, 2, 3, 4, 5, and then go 1, 2, 3, 4, 5, and then 1, 2, 3, 4. In which case it's like FIFO. Okay? So this is the case for here and here as well. So because also polling is used in these standards. So quality of service signaling. Do we have any signaling in 802.11? No. Here we don't. Right? For here, yes, of course. And we have, in each of these standards, we have two levels of scheduling, signaling. We have application level signaling and low layer level of signaling, or bandwidth requests. We talked about two levels in each of these standards. So here there are two levels, and here there are two levels. Okay? Admission control. Here there is no admission control. And here? There is? Well, there could be, but the standards does not define anything. Okay? The fact that you have signaling allows you to have admission control if you want, but the standards does not define it. Okay? The standards, again, it's polling can be used to either reject a node and have it completely out of the set. Okay? But the standards themselves, they do not provide any specific admission control. طيب بسم الله الرحمن الرحيم. It will come up eventually. I had a list of topics that I wanted to review, but unfortunately I left them, so I'll try to use my memory. So basically, as we said before, the course was divided initially into two parts. The first part was introducing you to quality of service in terms of a concept. What quality of service means, what are the different mechanisms that we need in order to assess and measure this quality of service. So this is the first part of the course. The second part of the course, what is the implication of this quality of service as a broad concept on almost all the protocols and layers and standards that we might or we may not have studied before. Okay? So at the beginning we talked about quality of service, we talked about what classification means in different layers, what is the channel access mechanisms, what are the different scheduling mechanisms, whether we use weighted fair queuing or priority-based queuing, and so on and so forth, right? And we talked about signaling, admission control, explicit or implicit admission control, and so on. So this is the first part of the course. Then in the second part of the course, we talked about the implications of these quality of service mechanisms in different layers. We started with the application and transport layers. So we talked about RTP, we talked about RTCP, and we talked about RTSP, and these different protocols, and whether we use these protocols for streaming stored multimedia or interactive multimedia applications like voice chats and so on and so forth, right? Then we covered the different aspects of quality of service in lower layers, and for that we have covered three sets of standards. The first one is Wi-Fi, right? And in Wi-Fi, as we said before, Wi-Fi was originally designed for data, so it was designed mainly for data, and with no quality of service mindset during the initial design of Wi-Fi. That's why DCF was suitable for Wi-Fi, because it has no overhead, right? No overhead in terms of synchronization, and the fact that you don't need any centralized controller to control who will have access to the medium at certain point in time, right? So in DCF, it's distributed, right? Distributed coordination function. So this is the main issue of DCF. DCF is distributed in nature, therefore you don't need any special overhead like certain gaps or synchronization or something like this between the different time slots. There is no actual time slot. So anyone is allowed to have access to the channel at any point in time. However, the pure sense of this is a protocol called Aloha, which is really very low efficiency, very low in terms of efficiency. So that's why in Wi-Fi they try to use the concept of sensing, right? So we have the cmpe482-2017-05-16, carrier sense multiple access, to try to reduce the collision, right? And with the sensing, we can raise the efficiency, because if you don't have sensing, then you will have lots and lots of accidents, right? So imagine if you have a roundabout with no particular precautions from the driver. So anyone who's going, he can just go without any precaution. So chances are there will be high probability of collision. And this probability will increase with the amount of traffic. So actually, if the traffic is very low, you don't actually need any sensing or anything, because the probability of collision will be very low. Because of this notion or fundamental concept in Wi-Fi, we have studied the fact that DCF is limited, or it actually falls short in terms of supporting quality of service, right? But that's fine for the Wi-Fi group. This was not the objective from the beginning, okay? And for this, they also left a placeholder by saying, okay, so we have an optional part of using PCF, right? So we have, so the frame in Wi-Fi is, first you have the preamble, and then you have DCF or PCF, right? And this boundary can move back and forth also, okay? So this can be actually 0, which means that PCF is optional. So you can have no PCF in the frame at all, right? But DCF is mandatory, so you have to have DCF, which means that the default channel mechanism in Wi-Fi is cmce. So channel mechanism is purely cmce. And using the carrier sensing, we can elevate and we can improve the efficiency of data transmission. And in fact, Wi-Fi, until recently, Wi-Fi was able to get data rates higher than metropolitan area networks and all other networks until recently. But because of some technologies in the physical layer like OFDM and things like that, and CDMA, these kind of standards, they have been able to reach to high data rates close to Wi-Fi, which makes really Wi-Fi less attractive recently. So DCF is purely based on carrier sensing, whereas this is based on pulling. And PCF is collision free, so you can have time slots in PCF, and these time slots, they get assigned to the different nodes based on unicast pulling. We did not talk about any broadcast pulling in that case. So PCF is purely collision free. And I'm trying to get to the answer of this question. This is one of the main differences. In Wi-Fi, we did not talk about multicast or broadcast pooling, in which case PCF is purely unicast pooling. Okay, so depending on this pooling sequence, we can give some guaranteed quality of service, or what we have called quantitative quality of service. However, the standard defines this, but it does not define any mechanism for providing this quantitative quality of service in any way. Okay? So they define the fact that PCF is based on unicast pooling, it's based on pooling. And it's up to you to design your pooling sequence in any way you see appropriate. So that's it. So, so each of these three standards, the chapters are organized in such a way that in the beginning, before we walk you through the quality of service and how it's implemented in this standard, first we have to introduce the standards. So for Wi-Fi, we talked about the first part, which we tried to give you some idea about the Wi-Fi standards in terms of DCF, PCF, what are the variations of this. So we talked about, for example, 802.11b, which is the baseline standard, and we said that this works on 2.4 gigahertz, right? And it uses data rates of like 11 megabits per second, around 11, up to 11 megabits per second. And we talked about, well, a different variation of this, which is 802.11g, which also uses this, but it can reach to a 54 megabits per second. So we were able to achieve higher data rates. Well, is there a way to improve that? Well, another group worked on 802.11a, which tries to use a different spectrum, which is 5 gigahertz, and it can reach to also 54 megabits per second. So these are different variations of the standards. All of them, they use these concepts. PCF and DCF. PCF is optional and DCF is mandatory. DCF is distributed. All of them, they use these same concepts, basic concepts. Which means that all these standards are not designed with quality of service in mind. Okay? Then, we studied these standards in terms of the fact that we can use DCF, and we studied the DCF in terms of so DCF works as follows. So you have any transmitter tries to sense the environment. So here is sense, and then if the outcome of this sense that the environment is idle, then what do? We wait for DIFS, and this is meant to avoid collision. So what are the different mechanisms or the different ways to reduce collision? Well, sensing is one. So when we sense, we try to avoid collision, but it does not eliminate it. So what else? DIFS. So when we wait for DIFS, depending on when the nodes will start the DIFS, one of them will gain priority and will gain access to the channel before the other, in which case this one will have higher priority and will have access to the channel. So the other one will come here, will try to sense the channel, it will find it busy, so it will stop. So after you wait for DIFS, then you have to sense again. Okay? Then, if it's idle, I waited already for DIFS, then I'm sure that the environment is available for me, so I can just send. When I send, do I send data? No, I send a RTS. That's a third level of trying to avoid the collision. So when I send this to a particular receiver, this receiver will wait for SIFS, and then it will send CTS. And here, all the other nodes will go into nav. Okay? And then when I send CTS, I wait for another SIFS, and then and only then I send the data. Then I wait for another SIFS here, and then I send acknowledgement. So whenever you hear any of this data and you're not engaged in this transmission, then you go into nav. Okay? Because some different nodes will listen to different types of these messages depending on where your location is, whether you are in the interference range or the transmission range and stuff, and what is the direction of this signal. So you may listen to RTS but not CTS, or the other way around. In which case, whenever you listen to any of these signals, you will go into nav, as long as you're not engaged in this transmission. So that protocol enables us to reduce the collision, and as we said, it does not eliminate it. So this is DCF. Other than that, PCF is very simple because it's based on pulling. So and pulling sequence controls everything. Okay. Other than that, the 802.11e introduced the concept of, instead of PCF, we use HCF. And instead of DCF, we use a enhanced DCF. Okay? And these two, they use the concept of priority and the concept of a service differentiation. From the beginning, our objective here is to address quality of service mechanism. For EDCF, we said that there is, instead of DIFS, we had a AIFS. So AIFS will have AIFS 1, 0, all the way to 7, to represent 8 different traffic classes. We call them traffic classes. Sorry, T. Not only that, we had the contention window size. Also, there is contention window 0 all the way to 7. What else? Persistent factor. Also persistent factor 0 all the way to 7. By specifying these 3 parameters, EDCF was able to achieve service differentiation. Okay? In terms of traffic classes, which means that EDCF can provide qualitative per class quality service. Right? HCF defines what we call a traffic stream or traffic spec, and this can be defined per flow. So for each flow, you can specify complete traffic specification as detailed as you want, and in that case, based on the fact that HCF is pulling based, so you can provide any granularity you want in terms of per flow, quantitative, quality of service for each individual flow using this T-spec. In terms of signaling, so what do we need in order to formulate this T-spec? Well, we need some information coming from these nodes. So these signals that come from these nodes in terms of bandwidth requests can actually take bardu one of 2 classes, either implicit or explicit. Implicit, which is what we have called it a Q state. So Wi-Fi calls it explicitly Q state indicators. In metropolitan area network, we called it slip indicator, which is the same. It's actually the same. Okay? So also for Wi-Fi, we use either Q state indicators for implicit quality of service, or explicit bandwidth requests, and for that we can use 3 ways. Also 3 ways in Wi-Fi, in Wi-Fi 802.11e. Either we send our bandwidth requests during HTF, in which case, I'm talking about the nodes in the uplink. We send our bandwidth requests either by implicit or explicit, doesn't matter. As part of HTF, in which case we use the contention-free period to send our bandwidth requests, or we send it in EDCF period, in which case it's contention-based bandwidth request, okay? Or we talked about a mode called a controlled contention, which is a small period of HTF in the middle of EDCF. So we talked about this mode, and we called it controlled contention. So that's the third way. It's actually collision-free in that case. as part of EDCF. We call it controlled contention. So these are the three ways how we can send our bandwidth requests to the access point in the case of 802.11e. Okay? Type. All right, so for metropolitan area networks, we said that for metropolitan area networks, this was originally designed for voice communications, right? And that's why, from the beginning, they took the quality of service concepts while they are designing this. And that's why the MAC, we talked about the MAC layer and the fact that it's connection oriented. So there is a connection ID, explicit connection ID. For Wi-Fi, the MAC layer is not connection oriented. DCF is not connection oriented. But whenever we talk about voice communication, we need some kind of circuit switching aspect, right? So that's why the MAC layer in metropolitan area network was actually connection oriented. Okay? Type. The physical layer is actually, we talked about some variations of these standards. So we talked about 802.16.1, which is line of sight, and it covers the specifications for one cell only. So there is no like co-location or anything. In Wi-Fi, there is the concept of co-location, and we talked about co-location. But here, there is no co-location. So it's line of sight from the nodes to the access point, and that's it. There is 802.16.2, which is an extension to provide some co-location. So basically, 802.16.2 was designed for co-location. So that's why this one, we talked about the fact that it's single carrier. So this is the only standard where FHSS is not there. Because Wi-Fi uses FHSS for co-location, right? So if you hop between the different frequencies, you will be able to mitigate and try to reduce the effect of interference between the cells that exist in the same location. But here, we don't have that, because basically we don't cover or we don't accommodate any co-location. So FHSS was not implemented. But in the physical layer, we had what we call burst, or burst profile. Okay, or adaptive burst profile. It's called adaptive burst profile. For the adaptive burst profile, we can actually change two things per frame. We can change the modulation scheme and the forward error correction scheme, right? So for the modulation scheme, we can use QPSK or 16 QAM or 64 QAM. And we said that as we go up, the spectral efficiency will be much, much higher. So we can fit and squeeze more data in the same symbol of modulation, right? However, when we do this, the distance between the different symbols becomes very short, and the probability of error will become very high. So we can be adaptive and smart. So when we see that the channel itself is good, so we can increase the spectral efficiency by increasing the modulation to 64 QAM or something. If the channel is bad, then the probability of error is high, which means that we need to go to QPSK in order to reduce the error probability. So this way we could be adaptive to the channel. And because here we're talking about metropolitan area network, the range is very far, right? So we're talking here about almost like 1 kilometer or at least 500 meters or something. So the amount of variations that might happen to the channel is high, right? Because the range is very far. And that's why this adaptive burst profile was part of the original part of the standard. It was not part of Wi-Fi or for Bluetooth. for Bluetooth, we talked about GFSK, right? Gaussian frequency shift key. But we don't have any adaptive Bose profile in that case. Okay, so this is the physical layer. And for MAC layer, we said that mainly we use TDD, TDMA, or FDD, TDMA. So for TDD, so this is for bidirectional communication. Okay? So by the way, for DCF, why we didn't talk about uplink and downlink? Well, for DCF, remember, all of us are the same, even the access point. The access point is one of the distributed nodes. So it can try to access the channel whenever it wants. And it can go through collision. Because DCF is based on distributed coordination. It's not based on centralized coordination. So whether uplink or downlink, it doesn't matter because the collision happens either way. But here, we're trying to eliminate collision completely. And one important thing we need to talk about here is if we're talking about FDD, then we need to have uplink and downlink in different frequencies. If we're talking about TDD, then we have to organize who will send in which direction so we can eliminate collision altogether. Right? So for TDD, so you have again the preamble, and then you have downlink subframe, and then uplink subframe. Okay? So that's for TDD. The frame is divided into two distinguishable subframes. And again, here we talked about the fact that this can be adaptive. This can be moved up, back or forth. And this way we could be symmetric in terms of providing uplink and downlink data rates. Or we could be asymmetric, which means that we can increase the data rate in the downlink more than the uplink. For some networks, this might be desirable because the amount of downloads on this type of network is more, in which case it's better to increase the downlink and reduce the uplink. So we'll move this way. Okay? Or we need to be symmetric, in which case we need to make this 50-50 kind of thing. Okay? So for channel access mechanism, we said that we have TDM for the downlink. And why we don't have the A is because it's always from the base station to all the nodes. So we don't need multiple access per se. That's why we called it multiplexing. So it's either sent to this node or this node or this node. It's multiplexing. It's not multiple access. Okay? And in that case, because it's from a centralized node to all the other nodes, we don't need any time gaps in between because synchronization is not an issue. The base station has only one clock, one centralized clock, and it can synchronize the time slots easily, right? Versus in the multiple access, that's in the uplink, here, in that part, it becomes a little bit more challenging, and that's why we need to have guard bands between the different time slots. And these guard bands account for any clock drift between the different nodes. Okay, so it facilitates the synchronization between the different nodes when they send uplink information to the base station. Okay, so to answer your question, now we'll zoom out to this guy. We will zoom out here. So first, here in the downlink, in each frame, the base station will send two things: the uplink map and the downlink map, right? So the downlink map, because both the downlink and the uplink, we're talking about time slots, and these time slots, they get allocated to the different nodes. Even in the downlink, I need to send node 1 or node 2 or node 3, right? So we have a base station, and we have different nodes. Right? So in the downlink, the direction is this way. I still need to allocate the time slots whether I need to send to node this node or this node or this node. مفهومة دي. Okay? So the same thing for the uplink, except that for the uplink it's a little bit more challenging because each node is sending independently and it doesn't know whether the other nodes are sending or not. So they need to be synchronized. They need to be well synchronized. Otherwise there will be collision and we'll go back to Wi-Fi. We don't want to do that. So, so this uplink map and the downlink map, this control information will be sent at the beginning of the downlink subframe. Because it's always sent from the base station to all the nodes, even for the uplink. Yani, the time slots in the uplink, it gets controlled by the base station. So at the beginning of the downlink subframe, the base station will send this downlink map and the uplink map. So the downlink map will send information about what time slots assigned to which node. So each one of these will say, okay, the first time slot is assigned to node 3. The second time slot is assigned to node 5, and so on. And in the uplink map, the same thing. Okay? This part of the question is solved? Okay? So the uplink and downlink map is clear. So now, in the uplink subframe, we can send information from any of the nodes to the base station. Now, for this uplink subframe, we talked about 3 different types of operations. We talked about the initial maintenance opportunities, contention request, and the granted time slots. Okay? We said that this is for both of these two, okay? These are, remember, these are mainly for signaling information. Okay? These 2 opportunities or durations could be collision based because they are a result of multicast or broadcast pulling from the base station to group of nodes or to maybe all the nodes. So during these 2 periods, okay, these are the result of the fact that the base station may send multicast pull to group of nodes or maybe to all the nodes. Same thing for the contention request. So what is the difference between the 2? Simply, the initial maintenance opportunities is for implicit kind of signaling, where you can either send uplink bursts just for the base station to do some measurements. Or you can send slip indicator, which is again the queue state indicator, to the base station. Except that here, during this period, the nodes will send their bandwidth requests, whether implicit or explicit, in a contention-based environment. Because if you send a multicast or broadcast pull in the uplink, naturally, we will have contention. Because remember, I did not allocate the time slots yet. That's what I'm trying to do. But in order for me to allocate the time slots, I need more information from the users. So there is an initial state that I have to go through these periods in order to get information from the nodes. Either indirectly, okay, or directly. But for both cases, they may contend and they may have collision. Okay? So I can get some explicit bandwidth requests or implicit bandwidth requests in this period as well. Okay? But in that case, it will be collision free. So this granted time slots is purely collision free. This is different from what Wi-Fi actually uses a little bit. So here, this part is a little bit different from what Wi-Fi uses. So here, I could have implicit bandwidth requests based on some slip indicators or some queue states. Here, I have explicit bandwidth requests, but also based on contention. And here, I could have also explicit bandwidth requests based on the fact that I allocate my time slot to send the bandwidth information, not to send data. Okay? And we said that this is based on unicast pull. So this and this is based on multicast or broadcast pulling. So I send broadcast message. Give me your quality of service requirements or bandwidth requirements. So in the uplink, the nodes will contend to give me back the information. Or I could actually send a unicast pull to a certain node, in which case the node will use its own time slot to send bandwidth requests. Okay? Why did I mention implicit here? Is because of a bandwidth stealing. So the node may use its time slot to send its own data, but use piggybacking with the data to send an incremental bandwidth request. Okay? So these are the different cases for sending bandwidth requests in the uplink. So in the uplink, we have these three phases. Two of them are based on contention. And the third one is contention-free. Okay? And all these phases can be used for explicit. This one is mainly implicit. This one is explicit. And this one is explicit or implicit, depending on whether you use piggybacking or not. كويس كده؟ Okay. طيب. So in addition to this, we have defined the different classes of service. For the case of Metropolitan, we have defined 4 different classes. We define UGS, or unsolicited grant service, and we have defined the real-time pulling service, non-real-time pulling service, and then best effort. So these are distinguished based on, we said that this one uses a fixed or a constant bit rate, and these ones, they use variable bit rate, right? And they also differ for the fact that this one, for real time, it supports basically multimedia content, whereas this is for FTP and kind of data communication. And they also differ in the different methods that they use for bandwidth request. And we talked about UGS using implicit only, so they use a lower slip indicator. Whereas for these, they use some kind of explicit bandwidth requests. Okay? But this one does not use explicit bandwidth requests based on unicast pull. So we talked about the different methods for requesting certain bandwidths for all these classes. Whenever we talk about classes, then, okay, that's good for quality of service. So we know that through these classes, we can provide some class-based or per-class kind of behavior for quality of service. So this will give us differentiated services, okay? Not necessarily quantitative quality of service. Because all the flows will go to the same class. So there is no way to distinguish between, except if you have a specific, if you use the polling mechanism to distinguish between the different classes, the different flows inside each class. Do we have a way to do that in Metropolitan Area Network? Yes. We have the connection ID, and that's why we said in Metropolitan Area Networks we have connection-based or connection-oriented MAC, so we have something called connection ID. So basically, if we look at the graph for a node in Metropolitan Area Networks, we see that you have different flows, and these flows are categorized as UGS, but each flow has different connection ID. So within that class, I can use the polling sequence, because at the time slots I can allocate it in any way, right? I can provide some distinction between these connections based on the connection request. So I can use the connection ID in the classification process. Okay? So there is a service flow ID, which basically refers to the class, whether UGS or RTPS or non-real time or something. So the flow ID will classify the incoming traffic to one of the traffic classes. But the connection ID can further be used to provide distinction between the different connections within each class. So if we want to provide per flow quality of service for metropolitan area, we can. But the standards does not provide any, again, mechanism in terms of what is the polling sequence, whether or not we have admission control or not. You are free to implement whatever you want. For the case of Bluetooth, instead of 4 classes, we talked about 2 major classes, which is synchronous connection oriented and asynchronous connectionless. And we said 1 class for voice communication and 1 class for data, because Bluetooth was designed for the 2 types of communication, for multimedia communication, using voice communication mainly, and for data communication as well. And we talked about the diverse set of services that Bluetooth can accommodate in terms of human interface device and RF COM, which emulates serial communication, and so on and so forth. For Bluetooth, we did not talk about different variations of standards. We talked about 802.15.1, that's it. We did not cover the other ones. Again, the physical layer is based mainly on 2.4 gigahertz. It uses FHSS, and it uses Gaussian frequency shift keying, only 1 bandwidth scheme. We can use different forward error correction schemes, but there's only one bandwidth scheme. Sorry, one modulation scheme. Okay? So we talked about the architecture for Bluetooth. We talked about piconets, scatternets, and how the node can be part of 2 piconets, and what is the implication of this on the frame structure, and so on. And for channel mechanism, for the case of Bluetooth, we said that, again, we use TDD, TDMA. There is no FDD. TDD, TDMA. But here, there is no distinguishable subframes. So for the case of Bluetooth, basically, you have even slots and odd slots. So the even slots are always from the master to one of the slaves. Okay, so these even slots are always in one direction, from the master to one of the slaves. And here, it's from one of the slaves to the master. So it's a mixed or interleaved kind of a TDD TDM. Okay, so this is the main difference between Bluetooth and. Other than that, there is a high level of similarity, in the sense that again here we use the different classes, but here we use 2 different classes. We use SCO, which is circuit switching, and we use ACL. So we talked about the fact that the slave node can have up to 3 concurrent SCOs, connections, in which case you can distinguish between different connections, okay, that belongs to the same class. So this is, again, per class quality of service, and it's quantitative because it's circuit switching, and you can pre-assign the time slots before you start communication, so you can guarantee quality of service. So it's connection-oriented, and it provides guaranteed quality of service. So for ACL, it's connectionless. So you can talk about a link, but you cannot talk about a connection. So there is no connection context per se. There is a link, and you can use the link manager to establish a logical link, but you cannot pre-assign time slots to this connection because there is no connection. So you can assign these time slots dynamically during the communication. And that's based on some signaling that can come from the nodes to request the bandwidth. Okay? So